Welcome to additional existence and uniqueness theorem examples. So let's go ahead and consider the IVP, y prime is equal to x squared plus y squared, all divided by sine of x, with the initial condition y of x naught equals y naught. So the first question we want to ask is, for what points x naught, y naught does a solution exist? So a solution exists. Oops, let me change colors. A solution exists as long as the function f of x, y equaling x squared plus y squared over sine of x is continuous in an open rectangle around x naught, y naught. So we just need to figure out where the function is continuous or where it's not continuous. So f is continuous everywhere except where we would divide by 0. So except where sine of x is equal to 0. I'm going to give myself a little bit more space. Again, this would result in we're dividing by 0, right, which we can't do. So sine of x equals 0 happens when x is equal to k times pi, where k is an integer. And so this is the only place where f is not continuous. So f is continuous everywhere else. So the IVP has a solution for all x naught, y naught, where x naught is not k times pi, where k is an integer. Anywhere else, we could come up with a little interval around x and a little interval around y, so that f was continuous on that entire rectangle. Then we want to ask, for what points x naught, y naught is the solution unique? So in this case, we need to check fy. So for unique, both f and the partial of f with respect to y must be continuous. On an open rectangle around x naught, y naught. So f of xy was x squared plus y squared all over sine of x. If we take the partial with respect to y, the x squared over sine of x doesn't have any y's, that'll just go to 0. The plus y squared over sine of x, y squared will go to 2y, and the dividing by sine of x just comes along for the ride. So once again, f is continuous Actually, I'm going to use a different color so it doesn't get too cluttered all in one color. So F is continuous. I can spell. Everywhere except x equaling k times pi, k an integer. Right, that results in dividing by 0 because sine of k times pi is equal to 0. Let me pause and update my screen. Now my screen has updated. Let's go ahead and look at that partial with respect to y. This again, the only issue we have is dividing by 0. Once again, that happens when x is equal to k times pi. So f, the partial with respect to y, is also continuous everywhere except when x is equal to k pi, k an integer. So what it means is we haven't changed where we're continuous. The partial with respect to y and f are both continuous at the exact same places. So we get the same location. So the IVP has a unique solution for all x naught, y naught, where x naught is not equal to k times pi, k being an integer. Let's go ahead and look at one more example. So let's consider the IVP y prime is equal to, in parentheses, x squared plus y squared, that whole thing times y to the 1/3, with initial condition y of x naught equal to y naught. We first want to know for what points x naught, y naught does a solution exist? So once again, existence just requires f of xy, which in this case is x squared plus y squared, whole thing multiplied by y to the 1/3, to be continuous. In an open rectangle around x naught, y naught. But that function f is always defined and is always continuous. Right? So f is continuous everywhere. So we have no problems. And so we get that the IVP has a solution for all x naught, y naught, no conditions required. Next up, we want to know where we have a unique solution. So in this case, again, uniqueness requires f and its partial with respect to y to be continuous. On an open rectangle. Around x naught, y naught. Again, I need to update my screen. I apologize. So we already know where f is continuous, right? So again, f of xy was equal to x squared plus y squared, the whole thing times y to the 1/3. And that's continuous everywhere. If we take that first partial with respect to y, the first partial with respect to y, we do the derivative of the first part with respect to y, so we just have 2y times y to the 1/3. And then we do the derivative of the second with respect to y. So we would look at x squared plus y squared times 1/3 y to the negative 2/3. So this y to the negative 2/3 is the only part that will give us some complications. Y to the negative 2/3 is undefined when y equals 0. So we get that fy is continuous everywhere except when y equals 0. So for existence, we just had to focus on f. We had continuous everywhere, so we always had a solution. For uniqueness, looking at that partial with respect to y, we have now added in that condition that y cannot equal 0 since f is not fy is not continuous there. And so we get that for our final solution, the IVP has a unique solution for all x naught, y naught, where y naught is not equal to 0. So essentially, we're looking for problem points where a function is undefined. Those are going to be our primary points where a function is not continuous. So this was, again, more examples using that existence and uniqueness theorem and finding if our initial conditions meet the requirements.